Okay, so I want to solve exercise 42 from section 7.3. And the reason I didn't formally write the problem down on the paper is because it's just to save a little time here, because I still want to get into section 7.4. What we can do is I'll bring up the example in your ebook, and you can go into your ebook as well, right? Okay, and I'm okay, so we're going to solve exercise 42 from section 7.3. All right, so let's go into the ebook then and look at this exercise. All right, so, and this is all being recorded, so, but go into your ebook. Perfect. Okay, and let's find the exercise. So click on chapter 7. Okay, 7.3, exercises. Okay, and let's get, hopefully it's exercise 42. It is. Okay, so now you can keep this in your web assignment, you can keep this example, out in front of you. But the problem is we have a sphere with a radius of 1 meter. Okay, a sphere with 1 meter radius has temperature 15 degrees Celsius. It lies inside a concentric sphere, okay, with radius 2 meters and temperature 25 degrees Celsius. So you have one sphere inside another. One has 1 meter radius, the other has 2 meter radius, and there's a temperature of 15 degrees on the smaller sphere and 25 degrees on the bigger sphere. The temperature T sub r at a distance r from the common center of the spheres, okay, so that's measured from the center of both the spheres, they have a common center. That temperature satisfies this differential equation, okay? Has anybody seen that in maybe a physics class or an engineering class? It might be a little bit advanced for physics 1, but has anybody, just out of curiosity, seen that kind of differential equation ever? And all right, all right. Well, it would make sense because you're learning it here. So, all right. So notice that we have here a second order differential equation. And in order to solve this, there's a little trick we can do. We can define S to be dt dr. Okay, this is a approach that is used to take a second order differential equation and break it down into a first order differential equation. And you see it has an application right here. So we want to do this and to find an expression for the temperature R, T sub R between the spheres. The temperature between the spheres is a subject of the radius, okay? How far out along the radius you are. Okay, so let's go ahead here and let's look at the solution. Okay, so here's that differential equation, that second order differential equation. We're letting S be E. We're doing a substitution, but not like an integral substitution. If we let S be the first derivative of t with respect to r, then we can rewrite this differential, this second order differential equation that has t as a function of r, as a first order differential equation that has s as a function of r. Because you see, the set d squared t dr squared is the same as d dr of dt dr. And that's the same as d s dr. And then the other part, of course, is, hold on here, one moment. The other part is just 2 over r times s. Are there any questions with the steps up to here? I'm sure you're going to see this when you take your differential equations class. You'll be you'll see this again. Okay, so now we have a first order. We have a differential equation that can be separated. 1 over s ds is equal to -2 over r dr. If you do a little work, separate the variables, you will get that. Okay. And now we're going to integrate both sides. Are there any questions? Okay, well let us proceed on then. Let us proceed on. Now keep in mind, ultimately, we're interested in t as a function of r. Okay, we're interested, make that nicer, t as a function of r. To answer the question, we need to find that formula. But we can solve for s and then backtrack. So here, the antiderivative of what s is the log of the absolute value of s, but we're able to assume here that s is greater than 0. In the context of the application, being that s is the rate of change of temperature with respect to the radius, that rate of change, that's going to be positive. In other words, the temperature function should be increasing with r, okay, without going into too much detail. If you look at the application, if you go back to the problem in WebAssign, it makes sense that t as a temperature as a function of the radius should be increasing. Hence, s, which is the derivative of t with respect to r, should be positive. And we know the radius is positive r. So here we go again. Similar situation to what we had in the last example. I have the log of s equals -2 times the log of r plus a constant. I'm going to exponentiate both sides. But I have to write the -2 times the log of r as the log of r to the -2nd. Okay, excuse me 1 minute here. I want to just put this phone in the other room. Okay, I have a landline at home, so it's not like it's not like a cell phone that I can mute. So, well, I have a cell phone too, but you know. Okay, so now the e to the -2 times the log of r is the same as e to the log of r to the -2nd. That's one of the log rules. If you have, you know, b times the natural log of A. That's going to equal the log of A to the bth power. Okay. All right. So, okay, now e to the c I'm going to call k. And then I got e to the log of r negative second. That's r to the negative second. So s is equal to k over r squared. S is equal to k over r squared. Are there any questions so far? All right, S is equal to k over r squared. Now what do you think we're going to do? We've solved for S. Now what are we going to do with S? What should we do with S? Remember, we're interested in this solution here, t as a function of r. That's right, John. Plug that derivative back in, and we'll do that. So S is equal to k over r squared. Now hold on here, one moment, let me, where is, yeah, there it is. Make this a little bit less. So now dt dr equals k over r squared, and now we can separate the variables on that differential equation so that we can solve for t. It's really a very beautiful problem. It really is. Okay, so now we have integral of 1 dt equals integral of k times r to the negative second dr. Okay, and you notice how I like to work vertically when I do my work. I see many of you working vertically, and like when you submit your work, you're working vertically. Okay, so let's continue. Let's continue. Now we just solve for t. Not hard to do. And all we have to do now, well, okay, so we have an indefinite intervals, right? So t will equal k times negative r to the negative first plus another constant a. We have to put another constant a there. So it looks like we have two constants to solve for. Two constants to solve for. If we have these two constants to solve for, k and a, how many initial conditions do we need to solve for those constants? That's right, John. We need two. And we have two. We have two initial conditions. You were told that and this here, right, this is T sub r. You were told that 1 meter away, the temperature was 15 degrees. So you can use that and get A in terms of K. Okay. Put this down a little bit. And then you're told that 2 meters away from the center, the temperature is 25 degrees. And that makes sense. Well, because you were told what the spheres were, the temperature of those spheres. So from that, you can determine then, you can solve for K. Okay, so the first initial condition allowed you to eliminate A. the second initial condition then allowed you to solve for k. So if 10 equals k over 2, k has to be 20. Are there any questions on that? Okay, well then let's move to the next page. If k equals 20, a is 35. Remember, this is our solution, but we have to solve for k and a. We found out k is 20. Well, if k is 20, then 20 plus 15 is 35. And so a is 35, and you have the answer. Okay, are there any questions on that? Okay, I'll stop the recording if there